Alright, so this is going to be section 3.2, and this time we're still talking about exponential and logistic model functions, but this time we're going to be talking about modeling with those. Everyone's favorite topic. So when we talk about exponential population models, they're always written in this form. If a population P is changing at a constant percentage rate each year, then we write it as P of t is equal to P sub 0, which remember is our initial value, times 1 plus r to the t. This is a parentheses. So I'll say it one more time. If a population P is changing at a constant percentage rate is r each year, then this is how we model that population, where P sub 0 is the initial population, and we express r, the rate, as a decimal. T, again, always time in years. If r is bigger than 0, so if we have r bigger than 0, then that means that P of t is an exponential growth function. On the opposite side, if we have r less than 0, then that means that P of t is exponential decay. So the first example that we're going to do with these types of problems is to be able to find the exponential growth or decay rate, that constant percentage. So here's your first example, and we're going to call this letter A. In letter A, they tell you that the population, P of t, is equal to 898,759 times 1.0064 to the t. That's the function that models our population. This is of San Jose, California. Now we want to find the constant percentage rate. So how do we do that? Well, we know that this value is actually our 1 plus r. So I'm going to go back. This value is our 1 plus r, so that means that we know 1 plus r is equal to 1.0064. Then if I subtract 1 from both sides, I get that r has to be equal to 0.0064. And since r is equal to 0.0064, we know that it actually is a growth because r is bigger than 0. We know it's a growth rate. Change that to a percentage. You have a growth rate percentage of 0.64%. Oh, sorry. Pretty easy, right? All right, let's try the next example. This is going to be the same thing. We're just going to call it letter B. And this time the problem is the population of Detroit. And that's modeled as 1,203,368 times 0.9858 t. So again, this is going to be our 1 plus r value. So 1 plus r is equal to 0.9858. Subtract the 1 from both sides. I'm going to get that r is equal to negative 0.0142. Because my r value is negative, that means that this is an exponential decay function, yes? So if this is an exponential decay function, actually I could scroll up a little bit, sorry. This is an exponential decay function. I want to find the rate of decay. So I'm looking for rate of decay. My rate of decay, if I move the decimal point over, is 1.42%. Now, why didn't I write negative 1.42%. Well, the reason for that is because we already know that it's a rate of decay. So we already know that we're going to be going down by a certain percentage. So we never actually write the negative when we talk about percents. If we were actually increasing, if this was an exponential function and it was growing, we would say rate of growth. So your final answer is never going to have a negative sign. What tells me that you know that if it's a growth or a decay is that you say rate of decay or rate of growth is this. Pretty simple, right? The next one is too. So let's look at the next example, and this time they give you a little bit of information, and this time you're finding the exponential function. So they say determine the exponential function with initial value, I'm going to write it as like this, initial value 12, and it's increasing at a rate of 8% each year. So what do we know? Well, we know that our function has to say p of t is equal to p sub 0 times 1 plus r raised to the t. So let's fill in what we know. We know the initial value is 12, so p of t is going to be equal to 12 times. We know our rate is 8%. So in decimal form, 8% is actually what? 0.08. When I add that to 1, I'm going to get 1 plus 0.08 raised to the t. And then I could go ahead and simplify that a little bit more and get p of t is equal to 12 times 1.08 to the t. And then you might want to just say that t is equal to time. This is your final answer. Sorry, these aren't absolute values either. These are supposed to be rounded. Questions? Hope not, because I can't answer them on a video. Here's the next problem. So now we're going to be talking about exponential growth and decay models. And you've probably done this. I know that we do this a little bit in Algebra 1 and Algebra 2. We're going to be taking it a step farther now in Pre-Calc. So given some information, we tell you that you are putting a culture of 100 bacteria into a petri dish. The culture doubles every hour. Predict when the number of bacteria will be 350,000. So our initial value, we start with 100 bacteria. The culture doubles every hour. And then the question is asking you, when will it be 350,000? We're going to get to that. We got to find the model first. So again, we have our normal function. P of t is equal to the initial value times 1 plus the rate. Oh, sorry. Not 1 plus the rate. We're just going to do the rate to the t. So now it's saying that it doubles. What does double mean? Doubles mean that it multiplies by 2. So we're raising 2 to some power. This is going to be p of t is equal to p sub 0 times 2 to the power t. Our initial value is 100, so you're going to do p of t is equal to 100 times 2 to the t. And then so we know that when t is 1, so after 1 hour, our bacteria population is going to be 200. I put 1 in here, and multiplying 2 times 100, I get 200. When t is 2, put 2 in for t, I get 2 to the second is 4. 4 times 100, 400. And I could do t is equal to 3. So see, I'm starting to get closer to that number that we're looking for is 350,000. That's what they want to find. When is that going to happen? Well, we got really small numbers now, but we're growing exponentially. If I substitute 3 in, I get 2 to the third power, which is 8 times 100 is 800. And you would keep going and going and going and going and going. So we know that we can write our model as this. but we want to find when it's equal to, t is our question mark, when is it equal to 350,000? So what I'm going to do is set them equal to each other. 350,000 equals 100 times 2 to the t. So we don't know how to solve this type of problem yet. So what you need to do on your calculator, under y1, in the y equals, under y1, you need to write the equation 100 times 2 to the x. Under y2 in your calculator, in y equals, you need to write the equation 350,000. Click graph, and you're going to get something that looks like this. This is our y2, this is our 350,000 line. This is our exponential function line. Where those two graphs are equal, or their intersection, is going to be your answer. And where those two graphs actually intersect is going to be 11.77, comma, 350,000. So that means that t equals 11.77 is approximately when our bacteria will reach 350,000. So that's approximately 11 hours and 46 minutes. Alright, we have two types of examples left. Radioactive decay. So we just did an exponential growth, and now we're going to do an exponential decay problem. In this problem, you have this, it says, suppose the half-life of a certain radioactive substance is 20 days. So this is our half-life, 20 days. We start with 5 grams of that substance. We want to know, when will there be 1 gram left? Okay, well, we got to model our function first. So over time, our initial value is 5 times. Since it's a half-life, we're going down by a half each time. It's decaying by a half. But this time it's not going to just be raised to the t. It's going to be raised to something else. T is actually the number of days. But it only goes down by a half every 20 days. Okay? So that means that if t is the time in days, t over 20 has to be the number of half-lives that we have. Half-lives. So instead of raising this to just t, we're going to be raising it to t over 20. The problem asks you, when will there be 1 gram left? Well, we start with 5. When will there be 1 gram left? So what we're going to do is substitute in 1 for our final answer here. 1 equals 5 times 1/2 to the t over 20. Same thing. You got to graph both equations. So you go to y equals on your calculator. Under y1, you're writing 5 times 1/2 to the t over 20. Under y2, you're writing the constant 1. When you graph that, it's exponential decay, remember, so your graph is going to look something like this, and you're going to have a constant at 1. This is your intersection here. Intersection is where they're both equal to each other, and we want to find when they're both equal to each other. That point actually ends up being about 46.44, comma 1. So what does that mean? Well, that means that t is 46.44. So if the question asks about how many days will it take for there to be only 1 gram of substance left, you would say 46.44 days. Or about 46 days and 11 hours. So those were all exponential examples. Now we're going to do one example of a logistic model. So this example Actually, I think it's a pretty neat example. It's modeling a rumor. So at a certain high school, there are 1,200 students. 4 students, Bob, Carol, Ted, and Alice, I don't know why they chose those names, but they did, start a rumor which spreads logistically at this function. So this is the spreading rate. 1,200 divided by 1 plus 39 e to the negative 0.9 t. That function models the number of students who have heard the rumor by the end of the day on day t. So we want to know by the end of day 0. End of day 0. So basically the end of the first day, but we call it 0. So we're trying to find s of 0. And that's really going to be the same as 1,200. Remember, anything, 0.9 times 0 is 0. Anything to the 0 power is 1. So this actually all just becomes 1. So then I have 1 plus 39, which is really 40. And that's really equal to 30. So the answer to your first question, how many students have heard the rumor by the end of day 0? 30 students. We're going to use that same function, except this time we're going to figure out how long does it take for 1,000 students to hear the rumor? How long does it take for 1,000 students to hear the rumor? So I want to be able to see our function there. So I want to set 1,000 equal to 1,200 over 1 plus 39 e to the negative 0.9 t. And what I'm going to do is graph this in my y1. And I'm going to graph this in my y2, and I'm going to get some kind of graph that should look something like a normal logistic function. Remember, we talked about logistic functions already. Should get something that looks like that. Where are they equal? They're equal where they intersect. They intersect at about 5.85, comma 1,000. So what does that mean? That means that t is approximately equal to 5.85. The question is asking you, how long does it take for 1,000 students to hear the rumor? In order for 1,000 students to hear the rumor, it will take about 5.85 days, or towards the end of the day on day 6. Make sense? Alright, that's going to be it for this video. We're going to do a lot of problems like this, modeling exponential growth and decay, in class next.